Hi everyone, and welcome to the first session of ENGR 315 lab tutorials. I am Arya, your TA, and I am going to be going over the lab exercises this term. First, we're going to discuss optical encoders. Encoders are generally used to measure the angular position of rotary devices. There are many types of encoders, but the one that is most common and is also used in the servo motors that we have are rotary incremental optical encoders. The measurement of angle in these encoders is relative to the last position when the encoder was powered. So basically, the encoder has a coated disc, as you can see, that is marked with a radial pattern. As the disc rotates, the light from an LED shines through the pattern, and it is picked up by a photo sensor on the other side. This effectively generates an on-off signal that can be counted to measure the angular position of the rotating shaft. On the right, you can see the compact version of the encoder. The encoder used in the Quanzer servos comes with three radial patterns of A, B, and the index. The A and B signals correspond to 512 lines on the disc, which have a 90-degree offset. The lines are equally spaced, and as the shaft rotates, with each pass, the index C signal occurs once per revolution, and it is used as a reference value for the calibration of the system. By using the offset between the A and B signals and also counting the trailing edge of each pulse in addition to the leading edge. So here's the trailing edge of each signal, and this is the leading edge of each signal. The number of counts for each revolution will be quadrupled, and thus the line patterns generate 2048 counts per revolution. This offset also allows the encoder to detect the direction of the rotation, as the sequence of on-off states differ for clockwise and counterclockwise rotation. Next, we discuss PWM, or pulse width modulation signals. PWM is a technique for getting analog results with digital means. The on-off behavior can be adjusted by changing the portion of time the signal spends on the on voltage, which is also known as the duty cycle. Here you can see three square waves with the same frequency, but each having a different duty cycle. So as we said, PWM signals help us generate analog behavior using digital means. As an example, let's say we want to generate a sine wave using PWM signals. It is obvious that the sine wave has a continuous form and therefore cannot be modeled with a solely on-off signal. In order to generate the sine wave, we need to discretize it into a number of equally distant sampling points and assign a duty cycle value to the sine value of each of these points. Let's say we have a sine wave with a period of 2 pi, and we sample 12 equally spaced points on it. We can generate a discrete approximation of the continuous sine signal by mapping the sine values for each of these sample points to a corresponding duty cycle value ranging between 0 and 100%, where a duty cycle of 0 represents the sine of 3 times pi over 2, which is -1, and 100% corresponds to the sine of pi over 2, which is 1. And all the sine values in between are mapped linearly. So in this course, we will be working with the Quanzer servo cubes, which would represent a dynamic system. As you can see, it is a cube. The components of the servo cube are a DC motor, a rotary shaft, and the magnetic disc that is attached on top of it. So our cube servo is connected via a USB cable to the computer, and we will be using the Simulink interface in MATLAB to communicate with this device. In order to create a Simulink environment, you need to open your version of MATLAB and click on the Simulink button right on top. We want to create a blank model to work with our device. Before communicating with the QUBE Servo, we need to make sure that it is powered on and connected to our computer. This is the Simulink environment that we will be working with to go through our experiments. In this blank space here, we will be creating a block diagram and import whatever blocks that we want to work with. So the first step when working with Quanser Servo cubes is to import the block which is called HIL initialize, which is an interface between the Simulink model that we will be creating and the QUBE Servo. In order to do that, we can use the library browser. So the first thing to mention is that these Quanser servos have their own specific blocks which have been pre-installed on the computer that I am using. But if you're accessing MATLAB from your personal computer, you would not have these blocks pre-installed. But don't worry, the exercises that we will be going through will only use the generic MATLAB and Simulink blocks and functions which you will have access to. So in order to import a block, as I said, you would be using the library browser, and you can look into one of these drop-down menus based on the type of block that you want to be using. The HIL initialize block is in the Quark targets drop-down menu, in data acquisition, and in generic configurations. And as you can see, I can now drag and drop the HIL initialize block to my Simulink environment and work with it. Now that I have my HIL initialize block, there are certain steps that I need to go through to configure the setup. First of all, I'm going to double click on the HIL initialize block to see what options I have. You can see the board name and the board type. So there are two QUBE servos that we're using here. There's QUBE Servo type 1 and type 2. Depending on the QUBE Servo type that we're using, we're going to select its corresponding board type. So the ones with the red strip are QUBE Servo number 2s. Therefore, I'm going to go ahead and find the corresponding QUBE Servo from the list. As you can see, QUBE Servo 2 USB is present here and is the QUBE Servo type that I'm going to select. And as you can see, as I clicked on the QUBE Servo type on the board type menu, the corresponding figure pops up in the HIL initialize block. So once the correct version of the QUBE Servo has been selected, we are just going to go and do a simple experiment to make sure that everything is intact and our device is communicating correctly with the Simulink environment. There are certain steps that we need to carry out before running each of our simulations. We need to first set default options. This is a step that we need to do for each time we want to use a Simulink block to connect to our QUBE servos and run a simulation. And then I'm going to again use the Quark tab and press build. You've got to press this build button whenever you make a change to your model. So whenever you import a block, remove a block, or change parameters within a block, you need to press that build button so that the changes take effect. And then after the model has been built, we want to deploy our code to our Quanser Servo so that we can run the simulation. In order to do that, I'm going to press download. So next, I'm going to start the simulation. You can see that the code will be compiled and there will be a time indicator, and as the time here goes forward, it means that the simulation is in progress. As you can see, the red strip on the QUBE Servo has turned green, and this means that the code is successfully being deployed and the simulation is being run. So I'm going to stop the simulation and go over to the next exercise, which is reading data from the encoder. So in this exercise, we will be using the encoder to read data from our Quark servo. And specifically, we'll be looking at the angular position of the shaft. So in order to do that, I will have to import a couple of blocks. First, I'm going to import the read encoder time base. By the way, if you know the name of the block that you want to import, you can simply double click on your Simulink model, enter the name of the block, and import it. So the next block that I'm going to use is a gain, and I'm going to type it in and import it. This is a lot easier than going through the library and importing the blocks by drag and drop. And then I'm going to use another block, display block, which we use to show the readings. The next step would be to connect these blocks together, and you can use your mouse cursor to do that. And this is basically the block diagram that we have. The HIL read encoder time base reads data from our Quanser servo, and then we'll multiply that by a gain value of 1, and the results will be displayed in our display block here in real time. So again, because I've made some changes to the model, what I'm going to do is to build the model again so that the changes take effect. Next, I'm going to download the code to the Quanser servo, and then I can press start. So this is the current angular position that is being read from our Quanser QUBE servo. If I rotate the disk on top, you can see that the reading changes depending on whether you're turning the disk clockwise or counterclockwise. The sign of the reading also would change. So next, I'm going to restart the simulation and measure the number of counts that I receive for each revolution. In order to do that, I'm going to press start again, and then by just eyeballing it, try to rotate it one round. So as you can see, the number which is being shown in the display block is 2091, which is close to the 2048 number of counts that we had previously in the background discussion part of the tutorial. So the next thing that we're going to do is to change the readings from number of counts to degrees. In order to do that, I'm going to adjust the value of the gain block by dividing it by 2048 and multiplying it by 360. The readings will now be measured in degrees. So I'm going to build the model and press start to run the simulation. Now, as you can see, if I rotate the disk one full round, approximately the reading that I get from the display block is somewhere around 360 degrees. So in the next exercise, we'll be driving the DC motor. In order to do that, I'm going to import an HIL write analog block and connect it to another block which will serve as our signal generator. I'm going to be using a constant block for this exercise. So basically what this constant block does is to generate a constant value, which I'm going to be setting equal to 0.5, which would indicate the input voltage that we'll be sending to our QUBE servo, and the HIL write analog will write the inputted voltage to our QUBE servo, and hence we will be able to change the velocity of the shaft. Next, I'm going to be creating a stall detection subsystem, which is going to prevent any harm to the servo. What it does is to monitor whether or not a input voltage is being applied to the servo and whether the shaft is rotating or not. So if the shaft is not rotating, but we have an input voltage to the servo, it means that something is keeping the servo from rotating. Maybe if you're holding a hand on top of the disc, and this might damage the motor. So the stall detection block will automatically stop the simulation so that no harm will happen to the servo. So in order to create the stall detection subsystem, I'm going to import a couple of blocks. First, the stall monitor, rate transition. I'm going to be using 2 rate transition blocks, so I might as well just copy paste this block, and you can do that by selecting the block and just as you normally would do with any type of text, Control V and Control C, you can copy or paste your block in the model. Then I'm going to connect these to the stall monitor block. There is a terminator block that needs to be imported as well, and a stop with message. Again, the stop with message block and the stall monitor are pre-installed blocks for the Servo QUBE, and you will not have access to them. So try not to find them in the library. Once I have all these blocks connected to each other, I can select all of them and create a subsystem. Creating a subsystem is just a way to avoid your main simulating model to be cluttered and does not really change the way that the model is being deployed. So the stall detection subsystem has got 2 inputs. I'm going to connect one of them to the input that is being fed to the QUBE servo and the other one to the readings from the servo. This is how the stall detection subblock can detect whether or not there is a voltage being inputted to the QUBE servo and whether or not the readings are changing. So next, I'm going to build the changes and try to run the model again. Okay. I'm going to click Start. As you can see, the disk starts to rotate, which means that the inputted voltage is successfully being transmitted to the QUBE servo, and the readings are changing accordingly. So the second exercise is filtering. We will be writing a voltage to the QUBE servo, and we'll be actually measuring the velocity from the other end. And one other thing that we want to go through is the effect of a low-pass filter in our readings. So there are a couple of new blocks that I have imported here. First, there is the sum block, which basically what it does is to sum up the signals that go into it. And there is a signal generator block, a inverse modulus, and a derivative. So a signal generator block is basically there to generate signals. There are a couple of attributes that you can change in it. First, the form of the wave that you want to be using, the amplitude, the frequency, and the unit of the frequency. So if you look at the tutorial, you can see the type of signal that we want to generate for this particular exercise, and you can find out what parameters we use in the signal generator block by playing around with it yourself and trying to get the readings to a scope perhaps. So another new block is scope, which I'm using twice in this model. First, after this sum block here, what it does is to basically plot the signals against time in the horizontal axis. So I have one scope here, which will show what the input signal to the QUBE servo is, and another block here, which will show the readings of the rotational velocity. So as I mentioned, there are two more blocks that we want to go through. First, there's the inverse modulus, which has a value of 2 to the 16. And this is basically the buffer size of our HIL read encoder. And there is also the derivative block, which takes the derivative of the signal that goes into it. So first, I'm going to run the simulation without using a low-pass filter and see how the readings will look like in the scope. So I'm going to look at the first scope, which is the input signal. You can see that it is a square wave alternating between 1 and 3 volts. There are a couple of options. You can fit the horizontal axis or the whole plot. The next scope that we have is the speed readings, which are pretty noisy right now. And we're going to deal with this noise by using a low-pass filter. So I'm going to stop the simulation and I'm going to add a low-pass filter now. And I'm going to do that by basically adding a transfer function. Transfer FCN is the block that I'll be using. Connect it. In the tutorial, it says that the cutoff frequency that we want to be using is 50. So I'm gonna use 50 in the numerator and S and 50 in the denominator. And there we go. We have the low pass filter. So next I'm going to build and press start. Now if I open the scope, which shows the angular velocity that our encoder is reading from the servo, you can see that it is a lot less noisy than the scope that we had before. So finally, we're going to see the effect of changing the cutoff frequency of our low pass filter in the output. In order to do that, I'm going to add another port to the scope and also create another transfer function, which would represent the other low pass filter that we'll be using. I'm going to use a cutoff frequency of 500 and see how it'll affect the readings. So I'm going to press build again and run the simulation. As you can see, the response, which corresponds to the lower low-pass filter with a cutoff frequency of 500, is noisier. This is because we're getting rid of a less proportion of frequencies compared to the one that we're using on the top of the figure. So the one on top will attenuate any frequencies higher than 50 rads per second, and the one below will attenuate frequencies above 500, which are less. That would be the end of today's tutorial. Thanks for tuning in, and see you in the next one.